Hey guys, hi, welcome back. So in this video, we will discuss about the singularity of a complex function. So this is going to be our topic. We will see what the singular point of a function is. We will see the types of singularity. The first one is the isolated and the second is the non-isolated. And further, we will see types of isolated singularity. As we know, there are three types of isolated singularity. The first one is removable, the second is non-essential, and the last one is the essential. All right. So this will be a definition based, and we will just see an example so that you will understand the definition much better. Okay. So first we will discuss singular point of a function. So when will be a function singular? Okay, what is singular point? If you have a function fz, and if that particular function fz, it is not analytic, all right, at a particular point, then that particular point is said to be singular point. You will say in definition, we can write it as the point at which a function fz is not analytic, is not analytic, is known as a singular point or singularity of a function. All right. So it is just simple. If you have a point and if the function is not analytic at that particular point, then you will say that particular point is a singular point, or you can say the singularity of a function. So for this, we will consider an example. All right. So if you have a function fz is equals to 1 by z minus 2. All right. So here you will see what? When z will be equals to 2, right? If z will be equals to 2, then fz will be what? Fz tends to infinity, right? That means it is undetermined. Then you can say it is having a singular point z equals to 2. Hence, z equals to 2 is a singular point. All right, where a function is not analytic, or you can say where the function is undetermined, means when for the particular value for which the function will tends to infinity. All right, that is the singularity of a function. Now you see the types of singularity. So there are two types of singularity. We will write here, there are two types of singularity. All right. The first one is what? The first is the isolated singularity. The second one is non-isolated singularity. All right. These are the two types of singularity. And the isolated singularity, it is further classified as isolated singularity is of three types. All right. So the first one is what? It is removable singularity. It is removable singularity. The second is the non-essential singularity. All right. And the last one is essential singularity. Clear? Now we will see first what is isolated singularity, and then we will see what is non-isolated singularity, and then we will go to the types of singularity. So for isolated singularity, first we will write the definition. Okay. So here what you will write, a point z equals to z naught is said to be isolated singularity if. So when will be a point z equals to z naught said to be a isolated singularity? So the first point is what? The first point is that fz is not analytic at z equals to z naught. Fz is not analytic at z equals to z naught. And the second is fz is analytic in the neighborhood of z equals to z naught. Fz is analytic in the neighborhood of z equals to z naught. That means there exists a neighborhood of z equals to z naught containing no other singularities. That is, there exists a neighborhood of z equals to z naught containing no other singularities. Okay, so to understand it much well, you have to understand that if you have z equals to a, all right, if z is equals to a, it is a singularity, all right, and if there is no other singularity in the neighborhood of z equals to a or z equals to z naught, whatever it is, okay, then you will say z equals to a, it is an isolated singularity, all right. If it is if a function is analytic only at z equals to z naught's neighborhood but not at z equals to z naught, okay, if you have a function z equals to z naught and if it is not analytic at z equals to z naught but in the neighborhood it is analytic, and if you are not having any other singularity in the neighborhood of z equals to z naught other than z naught, then you will say what? It is an isolated singularity. Or in other words, what you can say, that there is no other singularity within a small circle surrounding the point z equals to a. Okay, and this isolated singularity, you can say finite number of singular points also. That way also you can understand. So we will consider one example so that it will become much clear to you. So if you have a function fz is equals to 1 by z, all right. So if you see here, if you put z is equals to 0, right, z equals to 0, if you put z equals to 0, then this will become what? Infinity, yes or no? That means except z equals to 0, okay, it is analytic everywhere except z equals to 0, right? Because if you put z equals to 0, the function will be what? Undefined, right? That means it is analytic everywhere except z equals to 0. So z equals to 0, it is a isolated singularity. Okay, one more example, if you consider fz is equals to what? 1 by z minus 1, z minus 2. So if you see here, z is equals to 1, z is equals to 2. These are the singular points. These are finite singular points, right? So this is an isolated singularity. You can take isolated singularity is what? Finite number of singular points also, and non-isolated is what? Infinite number. That means there should not be any other singularities other than this, okay, in the neighborhood. Clear? Now we will see what is non-isolated singularity. So for non-isolated singularity, what you will say, a point z equals to z naught is said to be is said to be non-isolated singularity, all right, if the first is fz is not analytic at z equals to z naught, and the second is what? There exists a neighborhood of, there exists a neighborhood of z equals to z naught containing other singularities of fz, other singularities of fz. That means if there are a number of singularities other than z equals to z naught in the neighborhood of z equals to z naught, then it is called non-isolated. That means if you have infinite number of singularities other than z equals to z naught. So for this, if I consider one example, suppose you have fz is equals to what? 1 by sine pi by z. Now you see, when will be this function 0? It is undetermined. When will be sine pi z 0? See, sine pi by z will be 0 when pi by z it is equals to what? N pi, right? That will give you what? Z is equals to 1 by n, right? Because when this will be 0, fz will be what? 1 by 0 infinity, right? So when will be this function sine pi by z 0? When pi by z is what? When pi by z is equals to n pi. Yes or no? So n can take any value. It can be 0, 1, 2, anything. So from this you will get z is equals to what? You will get what? It will be 0, 1, 1 by 2, and so on. Right? Right? So that means you are having what? There are infinite number of singularities. Yes or no? Other than z equals to 0, it is followed up by what? A large number of singularities. Yes or no? So you can say z equals to 0 is a non-isolated. It is a non-isolated singularity. All right, it is a non-isolated singularity, okay, of the function, okay, of the function. Why it is a non-isolated singularity? Because z equals to 0, it is having infinite number of other singular points, okay. All right, so this is said to be non-isolated, and when you listen the word isolated and non-isolated, you can understand isolated means single, non-isolated means isolated means what? There should be one, and non-isolated means what? A lot, okay. That way also you can see. So you have to remember the isolated singularities are the finite number of singularities, all right, and non-isolated will have what? Infinite number of singularities other than one particular. That one z equals to z naught, it will be followed up by what? Other singularities of the function, okay, infinite, very large, okay, because you can see here n is very large na. Z equals to 0, it will have what? Very large number of singularities followed. So that is the reason that it is non-isolated singularity. Next we will see removable, non-essential and essential singularity. That is the type of singularities. But before going into the types of singularities, we will see the Lorenz series, because we have already discussed in the last class what is Lorenz series. So to discuss and to understand the removable, non-essential and essential singularity, we will have to write the Lorenz series. Now you see, if fz, it is an isolated singular point. It has an, if fz, all right, is an isolated singular, if fz has, okay, has an isolated singular point z equals to a, all right, then we can expand fz about z equals to a into Lorenz series expansion, okay, about Lorenz series. And how you can write it as, we know the Lorenz series expansion is what? Fz is equals to summation n equals to 0 to infinity, right? Here you are having an, and here you are having z minus a to the power n, plus summation, this will be from what? 1 to infinity, right? And bn by z minus a whole to the power n, and this term can be written as what? Bn by z minus a to the power n is there. You can write it as bn into with z minus a to the power minus n. All right. Now you see this second part. Okay, in the Lorenz series, this is the principal part of the expansion. This is the principal part of the expansion. So we will see this principal part of expansion and we will understand what is removable singularity, non-essential and essential. So the first is removable singularity. Okay. So in case of removable singularity, what will happen? If the principal part, okay, if this part is of the function fz about z equals to 0 has no terms, that means if bn is equals to 0, okay, in that case we will say z equals to a, it is a removable singularity. Okay, if the principal part, if you have a function, okay, fz, and if the principal part of the Lorentz series expansion of that function about z equals to 0, it is having no terms, that means what? Bn is equals to 0 for all n, then fz is having a singularity at z equals to a, and that singularity is termed is removable singularity. So what you will write here, if the principal part, okay, of the Lorentz series, if the principal part of the Lorentz series of fz about z equals to a has no terms, it has no terms. It has no terms means what? Bn is equals to 0, right? And this is for all n. Okay, this is for all n. Then fz has a removable singularity. It has a removable singularity. All right, it is having a removable singularity at z is equals to a. Clear? Or you can say in other word, one more way you can write it as if fz, okay, if at z equals to a, it is infinite. This is the or you can take. If fz, if you have the function as z and at z equals to a, if it is infinite, but when you will put limit z tends to a, it becomes finite. Then also you can say that it is a removable singularity. You can check in either way, but the most correct way is, and the most easy way, correct way, I won't say it, the most easy way is to use the Lorenz series. Okay, so in this case the Lorenz series will be what? So in this case you can write the function fz, the Lorenz series of the function fz equals to what? It will be summation n equals to 0 to infinity a n z minus a to the power n. All right, so this is removable singularity. That means there will be no term having negative power of 1 by z. Okay, 1 by z means z with negative power will be not there. All right, that means there will be no terms which is having 1 by z. Okay, because this is having the power of z as positive, the other one was having what? Negative. Now you can see one example also here. Okay, fz is equals to what? Sine z by z. Okay, so 1 by z I'm keeping as it is. Sin z can be expanded. You have seen in the first lecture, there I have written it will be z minus z cube by factorial 3 plus z to the power 5 by factorial 5 plus minus z to the power 7 by factorial 7 plus and so on. Now you see what you will get from here. If you see in this case, this will give you what? 1, right? Minus you will get what? Z square by factorial 3 plus z to the power 4 by factorial 5 minus and so on. If you see here, do you see any terms which is having negative power of z? No, there is no term 1 by z, na? Yes or no? So there is no negative term in the Lorenz series expansion. So you can say z equals to 0. It is removable singularity. All right? Because when you will put z equals to 0, this will be 0, right? So when you will get it to be what? 0 by 0. Yes or no? So you can say that z equals to 0, it is a removable singularity. You can do it in this way also. If I say the other way, this way, which I say, if you see, this will be what? Is z is equals to what? 0. When you put z equals to 0, you get fz is equals to 0 by 0. But that if you take limit z tends to 0, when it tends to 0, then you will get the value to be what? 1. Yes or no? That is a finite value, so it is a removable singularity. So this way you can see. Clear? That means it should not contain any term having 1 by z or any term which is having the power of z to be negative. That means the second part should be 0. Clear? Then it is removable singularity. So better you use the Lorenz series. All right. Now you see the non-essential singularity. So in case of non-essential singularity, what happens? The principal part of the Lorenz series expansion, it will above z equals to a, it will have finite number of terms. Okay. Let me write the definition so that it will become easy for you. If the principal part of the Lorenz series expansion of fz about z equals to a contains finite number of terms, okay, say m, all right, that is bn is equals to 0 for all n, m less than n, okay, then fz has a non-essential, it is having a non-essential singularity, or you can say a pole. Non-essential singularity is also said to be as pole. Okay, it is also said to be as pole. Okay, you can say it is a non-essential singularity or a pole of order m. Okay, at z equals to a. So if the principal part, you know, in the Lorenz series, what was the principal part? The principal part was bn, right? If that particular part in the Lorenz series expansion for a function fz about z equals to a, it is having finite number of terms. Okay, then you will say that z equals to what? A, it is a non-essential singularity. And see, finite number of terms is considered to be m, and it is for all n greater than m, bn will be equals to 0. Clear? So if you see, if I write here, in this case, the function fz is equals to what? So the first is what? N is equals to 0 to infinity, right? An z minus a to the power n plus summation. Now you see, initially when we saw the Lorenz series expansion, you saw it was n equals to 0 to infinity. But this time it will be up to m. N is equals to what? 1 to m, because it is finite. This is only the change. Okay, this is only the change. This is the thing to be noted. And rest is z minus a to the power minus n. Clear? So this only you have to see. This time what? The Lorenz, the principal part will have what? Finite number of terms. Okay, that is m. Here m, it is representing the order of the pole. Clear? Now if you see, if a pole is having order 1, okay, if you have a pole of order 1, then that is said to be what? Simple pole. Clear? This is said to be a simple pole. And you can say z equals to a, it is a pole. Here you are having z equals to a or not? Z equals to a, it is pole of order what? It is a pole of order m. Clear? And the Lorenz series expansion will be this. Now you can consider one example also here. We will see one example also. If you have fz is equals to what? 1 by z minus 1 z plus 2 whole square. So if you see the pole, z is equals to what? 1, z is equals to what? Minus 2. So if you see here z minus 1 whole to the power what? 1. So it is what? It is a simple pole. That means it is a pole of order 1. And z equals to minus 2, it is pole of order 2. Clear? So this is what you have to see. Just you have to see that the principal term will have what? Finite number of terms. That means now n will be equals to 1 to m. Clear? Last one, we will see the essential singularity. So essential singularity is nothing. In this case, you will see the principal partner, it will have infinite number of terms. So what you will write? If the principal part of the Lorenz series expansion of fz about z equals to a contain infinite number of terms. That means bn is not equals to 0. All right, for infinitely many terms. Okay, for infinitely many values of n, then fz has a essential, it has a essential singularity, okay, at z equals to a. All right, so when there will be infinite number of terms, that means bn is not equals to 0, then z equals to a, it is the essential singularity. You can have an example here. If you have fz is equals to what? E to the power 1 by z, right? You can see if z is equals to what? 0, then e to the power 1 by 0 is what? E to the power infinity. That means what? Infinity. This way also you can see, and you can see in one more way, you can just expand this one as what? 1 plus 1 by z plus 1 by z square 1 by factorial 2 plus z. So you can see what? 1 by z, you are having 1 by z or not? And the 1 by z is having what? Means z2 is having negative powers. Yes or no? And you are having such terms what? Infinite. It is continued. So you can say in this case z equals to 0. It is a essential singularity. Clear? So this is what you have to remember. So we have seen what, once again I will repeat here. We have seen first what we have seen what is singular. Just have a revision, okay, what we have done in this class. So singularity, we have seen singularity of singular point of a function is what? The point at which the function is not analytic. That point is what? Singular point. Clear? That means the function is undetermined at the point where the function is not determined. Okay, now you see, we will see isolated and non-isolated singularity. Isolated singularity can be said at what? Finite number of singular points, and non-isolated is what? Infinite number of singular points. That means if fz it is not analytic at z equals to z naught, and if fz is analytic in the neighborhood of z equals to z naught, means it is having what? No other singularities, okay, in the neighborhood of z equals to z naught, then it is isolated. And if it has what? Number of other singularities in the neighborhood of z equals to z naught, that means it is having infinite number of singular points, okay, then it is said to be non-isolated. Next we will see the removable singularity. So you have to just see the Lorenz series expansion, and you have to see that the principal part of this series, it will have no term. That means what? The principal part is 0. bn is 0 for all n. Second is what? Non-essential singularity. So for non-essential, it will have what? Finite number of terms will be there. That is bn is equals to 0 for all m less than n. Okay, and next you are having what? Essential singularity. For essential singularity, what you will have? It will be having what? Infinite number of terms. That means bn is not equals to 0. So you can just use the Lorenz series principal part. When you have a function, just expand and check. You can directly say either it's essential, it's non-essential, or removable singularity. So that's all in this video. Thank you so much. Have a good day.